right. So again, we are focused on this idea of finding particular solutions. So we no longer just have a zero here. We have some function g of t, which explicitly depends on t. And we need to figure out a particular solution that's going to satisfy this relationship. And keep in mind, we also have to get the homogeneous solution. We know now already how to get the homogeneous solution. We're going to use, first thing we're going to do is something called the method of undetermined coefficients. And it's basically, you're going to guess something, but you're going to guess things in the most general form and ask, how can I plug something in and get g of t in the end? And you got to shift your thinking to think about what happens. Oops, so ax p double prime plus bx p prime. What does this actually mean and what's going on? Okay. And the idea here is that we are going to basically take, given g of t, make a guess of some function and recognize that when we take derivatives of it and add it together, we are going to get some preordained result. Okay, so keep in mind. So we're going to take a function, and by take a function, you are going to have to make something up. We're going to then take derivatives, and then we're going to add things up. And we're not going to ask, how do I get g of t? We're going to ask, what do we get? How do we get something that's like g of t? Okay, and then we're going to go back and then clean up the mess so that we actually do get g of t. So instead of asking what function do we get, we're going to ask what kind of function do we get? And we're going to basically work this backwards. So before you ask this, you have to ask, what kind of function is g of t? Right, and it's a very different way than what the way we do things in calculus and other classes, is you're now thinking about types of functions and what happens in general as you manipulate these things. And so there's a couple things to keep in mind. First, if I take a polynomial of degree n and add a polynomial of degree n, what do you get? Well, you're going to get another polynomial, but the caveat is the highest possible degree you could get is n, but you might get a polynomial of lower degree. All right, so for example, if you take x squared plus 3x plus 5 and add minus x squared plus 6x plus 2, the x squareds are going to cancel, and I'm going to be left with 9x plus 7, so it's a polynomial of degree 1. It is not possible to take two quadratics and get a polynomial of degree 3. So you're going to get a new polynomial, and the biggest order it could be is the same order as what you started off with, but it could be less. If you take an exponential function and you add another exponential function, the result is an exponential function. So for example, if you take e to the 3x times 5 and add 8 times e to the 3x, you can get 13 e to the 3x. So those will stay the same. If you take a trig function and add a trig function, you're going to get a trig function. In particular, if you take a sine and add a cosine, you're going to get sine plus cosine. And this is going to be really important later when we start taking derivatives, that anytime you see a sine, you should subconsciously tack on a cosine in there as well and think that could possibly be part of your solution. And vice versa. If you see a cosine, you should think there might be a sine floating around because when you start taking derivatives, they're going to start popping up all over the place. So you should never let cosine be by itself. It needs a sine to be whole. Same thing with sine. It should never be by itself. You should also just assume there's a hidden cosine floating around somewhere. And then, suppose you have a top polynomial times an exponential, and you add another polynomial times an exponential. The result is going to be another polynomial times exponential. And the degree of this cannot be higher than the highest degree of these other polynomials. Okay. So for example, if you have 3x plus 1 times e to the 2x plus x to the 4th minus 3x times e to the 2x, you're going to have x to the 4th. Those are going to cancel. And a plus 1, so x to the 4th plus 1 e to the 2x. You have another polynomial of degree 4 times e to the 2x. And you should just be focused on that highest order that's possible. You should be thinking about that as a family of functions. Okay. So you need to build up a sense of a library of functions. And you should not be thinking about what's the derivative of a certain function. You should be asking, what kind of function do you get if you take a derivative of a different kind of function? So in general, if you take the derivative of t to the n, you're going to get a polynomial of 1 degree less. So when it comes to derivatives, a polynomial gives you another polynomial of 1 less degree. The derivative of an exponential is another exponential. So taking derivatives of exponentials just gives you more exponentials. And here's where it gets a little tricky. If you take the derivative of cosine, you're going to get a sine. And if you take the derivative of a sine, you're going to get a cosine. So this means that if you have a sine or a cosine or both, you are going to need to include both of those things. So if you just see a sine by itself, you should be thinking sine plus cosine. And if you see a cosine by itself, you should be thinking sine plus cosine. Okay. And then the last thing, and this is what's going to be important about this, is the product rule. All right, now the important thing here is I have to use the product rule because I have the product of two things. So when I do the derivative of this, I'm going to have the derivative of the first term times the second function plus the first term times the derivative of the cosine. So this could be a minus omega sine omega t. And now when I look at the second function here, I'm going to do exactly the same thing. Derivative of the first times the second plus the first function, and the derivative of the second is going to be omega cosine omega t. Notice I've got cosine times exponential. If I pull those things together, I get something times exponential times cosine. And the same thing here. Here I've got exponential times sine, exponential times sine. When I pull those together, I'm going to get a bunch of stuff times e to the mt sine omega t. So the way you need to think about this is if you see just one of these things, you should think you're going to need both of these because the derivatives are going to start popping up all over. And if you take a derivative of one of these things, you're going to get both. So derivative of exponential times cosine or exponential times sine is going to involve exponential times cosine times exponential times sine, and you need to be able to accommodate that together somehow. So you should always be thinking of these functions as working together and always having to be together. So anytime you see a function or non-homogeneous equation and you see a polynomial, you should be thinking, I'm going to have to deal with polynomials because the derivatives are polynomials. If you see an exponential, you should be thinking a solution is going to look like an exponential because when you take derivatives of exponentials, you just get more exponentials. Whenever you see a cosine or a sine or both, you're going to need to keep both of them together because the derivatives are going to be intermingled together. And the same thing when you see products. All right, so if you see a polynomial times an exponential, you should be thinking derivatives of that are going to give you polynomials times exponentials. If you see exponential times sine or cosine, you should be thinking about exponential times cosine and exponential times sine. So, again, we're assuming that we're going to have a linear equation, it's a differential equation, and it's not homogeneous. So there's some function of t, there's some explicit mention of g here. If g of t is a polynomial, you're going to make a guess that your particular solution is going to be polynomial. And you don't know what it's going to be in advance, but you should have some idea of the order of the polynomial. If g of t is order 3, you should be thinking a third order polynomial. And you're going to make the most general possible guess of what that means here. Then you're going to plug it back into the equation and see if you can then figure out what's going on. The other thing here is that, keep in mind, if I have two polynomials, and they're equal, suppose I say two polynomials of degree 4 are equal. The only way they can be equal is if the coefficients are the same. So C4 in this case must be 3. Likewise, the coefficient on the t cubed must be the same. Coefficient on the t squared must be the same. Coefficient on t must be the same. And the constant must be the same. Right? The only way two polynomials can be the same is if all the coefficients on those things are the same. Okay? Likewise, if g of t is an exponential, you're going to guess a general exponential. If there's a sine or cosine in there, you have to guess both cosine and sine, because when you start taking derivatives and plugging them back into here, they're all going to start flooding through. And you got to make the most general way to take a cosine plus a sine. And if your g of t is some polynomial times an exponential, you're going to guess a polynomial times an exponential and see what that means. Okay. And you're also going to have to be able to deal with combinations of these things. So suppose you have ax double prime plus bx prime plus cx is g of t. g of t is a polynomial of degree 5, your guess is going to be your particular solution is a polynomial of degree 5. If g of t is an exponential, your guess is that xp is going to be a very general exponential. If your g of t is an exponential plus polynomial of degree 5, then you're going to treat each of these separately. For this, you're going to use an exponential, and then for this, you're going to use a polynomial of degree 5, and you're just going to add those things together, plug them in, and ask, what does that imply? Okay. If g of t looks something like, let's call it mt plus b times sine of 3t, you're going to guess something that's going to look like, c1t plus c0 times sine of 3t plus b1t plus b0 times cosine 3t. And the reason why you want to guess something like this is because when you start taking derivatives of these things, you're going to get a linear function times sines and linear functions times cosines. And when you plug them back into the equation up there, you got to see what that implies about c naught c1, b0, b1 in terms of making things disappear. And again, you're going to end up with some polynomial times trig is going to equal your g of t. And the only way this can happen is if the coefficients on these functions are the same.